Picture this. A shadow passes overhead. You look up to see an eagle with a 3-meter wingspan diving at 80 kilometers per hour. Its talons are the size of tiger claws. It strikes a bird standing taller than a basketball hoop, driving those claws straight through bone with the force of a concrete block dropped from an 8-story building. This isn't fantasy. This happened. The Haast's eagle and the giant moa existed because when evolution gets trapped on an island, it rewrites its own rulebook. The pattern has a name: Foster's Rule. When large animals get isolated on islands, they shrink. When small animals get trapped, they grow into giants. It sounds simple until you see how extreme these changes become. Elephants that started at 10 tons ended up smaller than pigs. Eagles that weighed less than a house cat became apex predators capable of killing prey 30 times their weight. And the speed of these changes defies everything we thought we knew about evolution. But here's what makes this story urgent. Every one of these evolutionary marvels is gone, and the pattern of their disappearance reveals something unsettling about what happens when isolation ends and humans arrive. During ice ages, when sea levels dropped, land bridges emerged across the Mediterranean. Massive straight-tusked elephants, Paleoloxodon antiquus, wandered across these temporary highways. Standing nearly 4 meters tall and weighing 10 tons, they were among the largest land mammals ever to walk the earth. Then the ice melted, the seas rose, the bridges vanished, and populations of these giants found themselves trapped on islands like Sicily and Malta. What happened next challenges everything we understand about evolutionary time. These elephants didn't gradually adapt over millions of years. They underwent one of the most dramatic transformations in the fossil record. Paleoloxodon falconeri, the Sicilian dwarf elephant, stood just over 1 meter tall and weighed 250 kilograms. It had shrunk to less than 2% of its ancestors' body mass. The mechanism behind this incredible shrinkage involves something called pedomorphism. Evolution didn't redesign the elephant from scratch. It simply stopped development earlier. Adult dwarf elephants retained the proportions of baby mainland elephants: bigger heads relative to their bodies, shorter legs, and smaller tusks. They were essentially giant elephant babies that never grew up. The speed of this change is shocking. Fossil evidence suggests these elephants lost up to 200 kilograms of weight and 4 centimeters of height per generation. That's evolution operating at 200 Darwins, a unit measuring evolutionary change. For comparison, horse evolution over 50 million years averaged about 0.1 Darwins. On resource-limited islands, smaller bodies need fewer calories. Those who matured younger and at smaller size had the survival advantage. Size became a liability rather than an asset. Recent breakthroughs in studying fossil bone structures revealed something even more remarkable. These dwarf elephants didn't live fast and die young as scientists predicted. Growth rings in their bones show they lived for at least 68 years, far longer than their giant ancestors. They reached sexual maturity around 15 years of age and grew at a slow, constant rate throughout their entire lives. On a predator-free island with limited resources, a new strategy became optimal: slow, energy-efficient growth and a long, quiet life. But this adaptation carried a hidden cost. A species with such a slow reproductive cycle became exquisitely vulnerable to rapid change, turning a successful survival strategy into an extinction trap. 83 million years ago, a massive chunk of land broke away from Antarctica and drifted into the Pacific. This was Zealandia, a continent-sized landmass that carried almost no terrestrial mammals except bats. Today, 94% of Zealandia sits underwater, but New Zealand marks its highest points, and for 80 million years, this isolated continent conducted an extraordinary experiment. What happens when birds get an entire landmass to themselves? They become everything else. With no mammals to compete with, birds evolved to fill every ecological niche. They became the grazers, the browsers, the predators. They became an empire unlike anything else on Earth. The rulers of this empire were the moa. 9 species evolved to fill the roles that deer, cattle, and even giraffes occupy elsewhere. But these weren't just large birds. The South Island giant moa, Dinornis robustus, could stretch its neck to browse foliage 3.6 meters off the ground. Females stood 2 meters tall at the back and weighed up to 250 kilograms. But here's what made moa unique in all of bird evolution. They had no wings. Not small wings. Not vestigial wings. No wings at all. The fossil record shows only smooth shoulder bones where wing attachments once existed. No other bird lineage has completely eliminated all trace of wing bones. Moa achieved something unprecedented. They became the only birds to entirely abandon their aerial heritage. This wasn't gradual wing reduction like we see in ostriches or emus. This was a complete evolutionary erasure of flight. On an island without large predators, wings became not just unnecessary, but wasteful. The energy required to maintain flight muscles and hollow bones could be redirected toward growth and reproduction. Natural selection dismantled the machinery of flight, piece by piece, until nothing remained. The moa filled their world completely. Some species stayed small, occupying rabbit-like niches. Others grew massive, becoming the ecological equivalent of browsing elephants. They developed specialized beaks for different vegetation types. Some had long necks for reaching high branches. Others had shorter, more powerful necks for ground feeding. But every ecosystem needs predators, and into this world of flightless giants came something extraordinary. Genetic analysis reveals its humble origins. A small raptor, closely related to Australia's little eagle, somehow crossed the Tasman Sea. This bird weighed less than 1 kilogram. It found a land with no competing predators and an abundant food source in the form of giant flightless birds. In under 2 million years, this small eagle transformed into Haast's eagle, the most powerful aerial predator that ever lived. It increased its body mass by 10 to 15 times, reaching weights of up to 17 kilograms, with a wingspan of 3 meters. But size alone doesn't capture what made Haast's eagle remarkable. Its entire anatomy was redesigned for killing prey many times its own weight. Its legs were massively muscled, proportionally larger than any modern eagle. Its talons reached 9 centimeters in length, the size of tiger claws. Its beak was built not for tearing small prey, but for crushing skulls. The hunting strategy was devastating. Haast's eagle was an ambush predator. It would perch high on cliffs or in trees, then launch itself at moa at speeds approaching 80 kilometers per hour. The impact force has been compared to a concrete block dropped from an 8-story building. Multiple moa pelvic bones have been found with distinctive puncture wounds that perfectly match Haast's eagle talons. The eagle struck with enough force to shatter solid bone, driving its claws deep into the moa's pelvis and back. One talon would anchor in bone, while the other crushed the skull with immense grip strength. This wasn't the hunting strategy of any modern eagle. Modern eagles snatch prey and carry it away. Haast's eagle was more like a feathered lion. It killed where it struck and fed on carcasses too large to lift. The relationship between the moa and Haast's eagle represents evolution's arms race in perfect isolation. The gigantism of the moa provided the selective pressure that drove the gigantism of the eagle. The eagle's lethality influenced moa behavior, and possibly their size distribution across different habitats. But this specialization created a fatal vulnerability. When Polynesian settlers arrived in New Zealand around 800 years ago, they found a world of giant flightless birds. Within 2 centuries, all 9 species of moa had been hunted to extinction. Haast's eagle, completely dependent on moa for food, starved and vanished immediately afterward. An 80-million-year evolutionary experiment ended in less than 200 years of human contact. In 2003, archaeologists working in the cool darkness of Liang Bua Cave on the Indonesian island of Flores made a discovery that would rewrite human evolutionary history. They unearthed a skeleton designated LB1 that defied every expectation about our lineage. The individual was an adult female who stood just 1.1 meters tall and weighed an estimated 25 kilograms. But these weren't the proportions of a child or someone with a growth disorder. The wisdom teeth were fully erupted. The pelvis showed signs of childbirth. This was a mature member of a species that had evolved to be smaller than most 10-year-old children. Even more shocking was the skull. It housed a brain with a volume of only 420 cubic centimeters, roughly 1/3 the size of our own, and comparable to a chimpanzee's. Scientists had discovered a human species that seemed to violate the fundamental narrative of our evolution, the relentless march toward larger brains and greater intelligence. They named it Homo floresiensis. The media called it the Hobbit. Initial skepticism was fierce. Some researchers insisted the skeleton represented a diseased modern human suffering from microcephaly or another developmental disorder. But then more individuals were found. 15 partial skeletons, all showing the same tiny stature, the same small brains, the same unusual mix of primitive and advanced features. The dating shocked everyone. The youngest Homo floresiensis bones date to 50,000 years ago. The oldest stretch back 100,000 years. Stone tools associated with them extend back 190,000 years. At nearby Matamenge, even older ancestral remains have been found, dating to 700,000 years ago. This timeline creates a profound paradox. Homo floresiensis lived on Flores for at least 600,000 years. During that same period, our own species evolved in Africa, developed language, created art, and began spreading across the globe. While we were becoming modern humans, Homo floresiensis remained essentially unchanged on their isolated island, tiny-bodied and tiny-brained, making the same stone tools generation after generation. But here's where the story becomes truly remarkable. Despite their diminutive brains, these hobbits were far from primitive. Analysis of their skulls reveals that the prefrontal cortex, specifically the area associated with complex planning and problem-solving, was proportionally similar to our own. The archaeological evidence supports this anatomical finding. Homo floresiensis manufactured sophisticated stone tools that closely resemble those made by early modern humans in nearby regions. They controlled fire, as evidenced by charcoal layers in the cave. Most remarkably, they hunted. At Liang Bua, cut marks on bones of the island's dwarf elephant, Stegodon florensis insularis, are found directly associated with clusters of Homo floresiensis stone tools. The positioning of these cut marks shows systematic butchering patterns. These tiny humans knew exactly how to dismantle an elephant, even if it was only pig-sized. The hunting evidence is compelling. Stegodon bones from juveniles show the most cut marks, suggesting Homo floresiensis targeted younger, more manageable prey. But even juvenile dwarf elephants would have weighed several hundred kilograms. The image is extraordinary. Meter-tall hunters with chimpanzee-sized brains, cooperatively taking down animals many times their own weight. Their origins remain hotly debated. They may have descended from Homo erectus populations that reached Flores and underwent extreme dwarfism, shrinking from 1.8 meters to 1.1 meters in height. Or they could be remnants of a much earlier, more primitive migration out of Africa, meaning small-brained hominins were spreading across the world far earlier than we ever imagined. Regardless of their ancestry, Homo floresiensis represents the ultimate proof that our own lineage is not exempt from the fundamental ecological pressures that shape all life. The human brain consumes about 20% of our body's energy. On a resource-poor island, it becomes a significant metabolic liability. The dramatic brain reduction in Homo floresiensis mirrors what happened to other island species. Evolution eliminated expensive, unnecessary features. This discovery shatters the narrative of human evolution as inevitable progress toward larger brains and greater intelligence. It reveals that even our most defining characteristic is subject to the same evolutionary forces that shrunk elephants on islands worldwide. The Hobbits disappeared around 50,000 years ago, coinciding with the arrival of modern humans in Southeast Asia. The pattern is achingly familiar. When isolation ends, the unique evolutionary experiments of islands come to an abrupt end. During ice ages, when sea levels dropped 120 meters below today's levels, Australia and New Guinea fused into a single, massive continent called Sahul. This supercontinent, isolated for 30 million years, became evolution's laboratory for an entirely different mammalian experiment. While placental mammals dominated other continents, marsupials ruled Sahul. They evolved into forms that filled every ecological niche, creating parallel solutions to the same survival problems through completely different evolutionary pathways. The result was a menagerie of creatures that defied imagination. The undisputed giant of this lost world was Diprotodon optatum, essentially a wombat scaled up to rhinoceros proportions. Standing 1.8 meters at the shoulder and stretching nearly 4 meters in length, Diprotodon weighed up to 3 tons, making it the largest marsupial that ever lived. But size alone doesn't capture what made this creature remarkable. Diprotodon's anatomy reveals a unique solution to supporting massive weight. Its limbs splayed outward from its body in a sprawling posture unlike any large mammal today. It walked on its palms and heels in what scientists call extreme plantigrady, essentially developing heel-like structures in both wrists and ankles. Trackways show no claw or toe impressions because these digits were lifted off the ground, while the broad palms and soles distributed the enormous weight. This gave Diprotodon a stable but shuffling gait, perfect for migrating long distances across Australia's increasingly arid interior. With continuously growing teeth, it could process the toughest drought-resistant vegetation. Imagine herds of these giant wombats lumbering across Pleistocene Australia like living bulldozers, reshaping the landscape simply by their passage. But every ecosystem needs predators, and Sahul produced one of the most unusual carnivores ever to evolve. Thylaccoleo carnifex, the marsupial lion, weighed around 130 kilograms and possessed an anatomy so bizarre it almost defies comparison to any living predator. Thylaccolleo's signature feature was its dentition. Instead of the long canine fangs of true cats, it had enormous blade-like premolars that worked like bolt cutters. The third premolar on each side was honed into a scissor-like carnassial, capable of shearing through hide and bone. Its front incisors were enlarged, like rodent teeth. In effect, Thylaccoleo had jaws that functioned like giant tin snips, a uniquely marsupial solution for being a hypercarnivore. Its bite force was extraordinary, estimated to match that of an African lion, despite Thylaccolleo's smaller size. But its most distinctive weapons were its forelimbs. It possessed a partly opposable thumb, armed with a massive hooked claw, presumably used to grapple prey or deliver disemboweling strikes with rabbit-like kicking motions. Paleontologists believe Thylaccoleo was an ambush predator. Its limb proportions and muscular tail suggest it wasn't built for sustained running, but for explosive power and possibly climbing. It may have waited in trees or dense brush, then leaped onto passing prey like giant kangaroos or juvenile Diprotodon, slashing with those fearsome claws and delivering a crushing bite to the neck. It was a marsupial experiment in carnivory that armed itself with bolt-cutter teeth and switchblade thumbs. No living predator employs anything like this hunting strategy. The reptilian contingent was equally impressive. Varanus priscus, commonly called megalania, was essentially a Komodo dragon scaled up to crocodilian proportions. Conservative estimates place it at 5.5 meters in length and 500 kilograms in weight, making it the largest terrestrial lizard known to science. Some earlier estimates suggested even larger dimensions, but current evidence favors this still enormous size. Like its smaller varanid relatives, Megalania was likely venomous, delivering septic bites that weakened prey over time. It would have been a top predator of Pleistocene Australia, capable of taking down large marsupials or scavenging carcasses that even Thylaccoleo couldn't finish. With serrated teeth and a powerful body, it represented Australia's Mesozoic heritage persisting into the Quaternary. Then, around 42,000 years ago, this entire world vanished. In geological terms, the extinction was instantaneous. Every land animal over 44 kilograms disappeared within a few millennia. The timing haunts paleontologists, because these animals had survived previous ice ages, volcanic eruptions, and dramatic climate shifts for millions of years. The extinction coincides almost exactly with human arrival in Australia, dated to between 50,000 and 45,000 years ago. But here's the puzzle that has divided scientists for decades. Unlike North America, where Clovis kill sites with butchered mammoth remains are common, Australia has yielded almost no direct evidence of humans hunting megafauna. No kill sites, no butchered Diprotodon bones, no spear points embedded in Thylaccoleo ribs. The smoking gun is missing, leading to more subtle explanations for the catastrophe. The most compelling theory involves landscape transformation through fire. Early Aboriginal Australians practiced fire stick farming, regularly burning vegetation to promote grass growth and aid hunting. This continent-wide ecosystem engineering converted forest and shrubland mosaics into more open, fire-prone environments. Such habitat transformation would have been devastating for large browsers like Diprotodon, which depended on diverse vegetation. The land's carrying capacity effectively shrank through human fire management, leading to population crashes without requiring systematic hunting. Evidence supports this. Dramatic shifts in plant communities and crashes in megafauna dung fungus spores around 45,000 years ago coincide with increased charcoal and sediments. Small changes in fire frequency and habitat structure multiplied across thousands of years, ultimately bringing down giants that had ruled their continent for millions of years. The principles that created dwarf elephants and giant eagles aren't confined to remote islands or ancient history. Today, human activity is fragmenting continuous habitats into isolated patches at an unprecedented scale, effectively turning the entire planet into an archipelago of habitat islands. A landmark 2015 global analysis revealed that 70% of the world's remaining forests now lie within 1 kilometer of a forest edge. We are creating the exact conditions that historically triggered Foster's rule. Small, isolated populations cut off from gene flow, facing novel selective pressures in resource-limited environments. The evolutionary responses are already visible. On the Philippine island of Mindoro, the critically endangered tamaraw represents a living example of island dwarfism. This buffalo weighs only 21% as much as its mainland water buffalo relatives, having evolved in isolation to fit the island's carrying capacity. In the Florida Keys, key deer have been reduced to roughly half the size of mainland white-tailed deer. On Caribbean islands, multiple deer species have independently evolved smaller body sizes. The pattern repeats wherever large mammals become isolated on small land areas. But modern fragmentation operates at a speed that outpaces evolution's ability to respond. Contemporary habitat destruction happens within decades, not millennia. Species face the selective pressures for dwarfism without the time needed for evolutionary adaptation. The primary outcome isn't adaptation, it's extinction. Habitat fragmentation now ranks as a leading driver of global biodiversity loss, reducing species diversity by 13% to 75% in the fragments studied. The current extinction rate is estimated at 10 to 100 times the natural baseline, with approximately 1 million species now at risk. We have accelerated the conditions that historically produced evolutionary marvels into a mechanism for mass extinction. The island rule that once created giants and dwarfs now operates in a world where isolation means death rather than diversification. The same forces that gave us Hobbits, eagles, and Hobbit humans are now driving species toward oblivion before they can adapt to their shrinking worlds. These lost worlds prove that evolution operates on timescales we can actually observe. When isolation removes the mainland rules, life races toward extremes in geological eye blinks. The dwarf elephants of Sicily shrank by 92% in just 8,000 years. Haast's eagle exploded from house cat to apex predator in under 2 million years. Even our own species underwent dramatic dwarfism on Flores, creating humans with chimpanzee-sized brains who still manage to hunt elephants. But every one of these evolutionary experiments ended the same way. The arrival of modern humans marked the beginning of the end. Maori settlers exterminated all 9 moa species within 200 years. Haast's eagle followed immediately after. The Hobbits of Flores vanished exactly when our species reached Southeast Asia. Australia's marsupial giants disappeared within millennia of human arrival. The pattern is unmistakable and urgent. We are now creating island conditions everywhere through habitat fragmentation. 70% of remaining forests sit within 1 kilometer of an edge. We've turned the planet into an archipelago of isolated populations, facing the same selective pressures that once created biological marvels. The question isn't whether modern fragmentation will produce evolutionary surprises. It will. Foster's rule doesn't stop operating because we've entered the Anthropocene. The question is whether anything will survive long enough for those surprises to emerge, or whether we'll drive species extinct before isolation can work its transformative magic.